Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing tunnels, their concepts and configurations in Junos. In this lesson, we'll be taking a close look at GRE tunnels in Junos. We'll review what a GRE tunnel is, and even take a close look at a packet capture of traffic which has been encapsulated in a GRE tunnel. Then we'll do a deep dive into the GRE header format, and finally review the commands needed to configure a GRE tunnel in Junos. So let's get started and first jump into a quick refresher on what a GRE tunnel is and why it's used. GRE stands for Generic Route Encapsulation. GRE was originally defined in RFC 1701, though the current version of GRE most commonly used is defined in RFC 2784. GRE was created to allow tunneling of arbitrary protocols within an IPv4 header. GRE can encapsulate IPv6, MPLS, other IPv4 packets, and more protocols within an IPv4 protocol header. This can allow various network domains to be extended across an intermediary network, which doesn't support the protocol used at the edges. For example, two sites in your enterprise which have been migrated to IPv6 may need to communicate with one another, though are separated by an IPv4 only core. In this case, a GRE tunnel could be used to bridge those IPv6 domains across the IPv4 domain. Now that we have a good understanding of what GRE is used for, let's take a look at what a packet which is encapsulated using GRE looks like. As we saw in a previous lesson, not only is the inner protocol encapsulated in an outer IP header, but it also typically has a tunnel header as well. In this case, it's a GRE protocol header, and that header is 8 bytes long. In the case of the common GRE protocol used today, which was defined in RFC 2784. However, extended GRE was another addition to the protocol, which was defined in RFC 2890. This version of GRE uses a 16-byte header, which adds a couple of fields, namely the key and sequence fields. In the screenshot at the bottom, we see an ICMP packet, a ping reply specifically, which is encapsulated by GRE. We have the decoded protocol headers in the bottom half of the screenshot. The first header we have is the Ethernet frame header, as is expected. The next header is the outer IP protocol header. We see this has a source address of 10.0.0.2 and a destination address of 10.0.0.1. The next header field is the GRE protocol header. As we'll see in the following slide, the GRE protocol header includes a field for defining what protocol is being encapsulated. In this case, we see that an IPv4 packet is being encapsulated. The inner IP header has a source IP address of 10.1.1.2 and a destination address of 10.1.1.1. Then, finally, in the payload of the packet, we have the ICMP protocol information. In this case, a reply message to an ICMP echo request, also known as ping. Great. Let's now zoom in a bit and take a closer look at the GRE protocol header fields. At its core, the GRE protocol is pretty simple. The first bit is the C bit. This is a flag that defines whether a checksum field is present or not. If it's set to 1, there is data in the checksum field and should be used for error checking. If it's set to 0, then the protocol should ignore the checksum field as data is not included there. The following 12 bits are reserved. The next 3 bits define the version of GRE in use. The following 2 octets, or 16 bits, are used to define what protocol is being encapsulated. It's not a coincidence that this field is the same length as the ether type field in an Ethernet header, as this field follows the same format as the ether type field to define what protocol is being encapsulated and therefore can give any value defined as an ether type. The next 2 octets contain the checksum, used for error checking to validate the integrity of the packet to ensure it was not degraded or otherwise malformed through transmission. The final 2 octets are reserved as well for future use. Excellent. Now that we have a solid understanding of the structure of the GRE protocol, let's take a look at an example configuration of a GRE tunnel on a pair of Junos routers. In this example configuration, we have VSRX1 and VSRX2. The physical interfaces connecting the devices are on the 10260/30 network. These devices, however, have an IGP configured, which allows them to have loopback connectivity. The VSRX1 tunnel configuration is shown on the left, while the VSRX2 tunnel configuration is on the right. We see that both have a GR interface configured, and the configuration is occurring in the logical unit 0. Within the logical unit, we have both INET protocol family configuration and tunnel configuration. Within the tunnel configuration, we simply have a source and destination IP address. These must be addresses which are reachable outside the tunnel. You'll notice that these source and destination addresses are the loopback interfaces of the routers, shown here. Since the devices have an IGP in place, they have loopback connectivity over the intermediary network. This is the same configuration used when reviewing the packet capture 2 slides ago. This tunnel creates the 10110/30 network. If a packet is received by VSRX1 from some local device and the destination has a next hop of 10112, then the packet will be encapsulated and sent over the tunnel to VSRX2, since 10112 is reachable over the tunnel interface. Note, of course, that this configuration is completely stateless. As long as the tunnel is configured, it will be in an up state. We have no assurance that the destination will receive the encapsulated packet, or that it will know how to decapsulate it once received. And that's it for GRE Tunnels. I appreciate you reviewing the GRE protocol details and format with me, and the example configuration of a GRE tunnel on a Junos device. I hope that this lesson has been informative for you, and I would like to thank you for viewing.